First off, the definition of linear. Remember, a linear equation is an equation with no powers. So if you look at this, this is a linear trigonometric equation because my cos x is not squared or cubed, no powers. So first we're going to treat this as if cos x was, say, a w. If this said negative 2w equals root 3, in order to isolate for this, you would divide both sides by negative 2. And that's what I've done. In simplifying, we get cos of x equals negative root 3 over 2. This ratio should look familiar. We don't want to plug this into our calculator because we can get an exact value. This is one of the ratios that results from my special triangles. If we look over here, pi over 6. Cosine of pi over 6, the adjacent over the hypotenuse, is root 3 over 2. So cosine of pi over 6 is root 3 over 2. What does that have to do with this? This is negative, which means our answers are going to be in the quadrants in which cosine is negative, the sine quadrant and the tangent quadrant. So typically, we'll be getting two answers in two different quadrants. The pi over 6 comes in as the related acute angle or the reference angle in here. Remember, we always draw those angles relative to the x-axis. So we have some angle in the sine quadrant with related acute angle pi over 6. Now, in order to calculate that, we have to remember how to add and subtract fractions. We're looking for an angle where I start at pi and I sort of backtrack pi over 6, this mystery angle here. So pi, take away pi over 6. I've made a common denominator here. 6 pi over 6 is the same as pi. Subtracting, my final answer is 5 pi over 6. This angle in the sine quadrant with related acute angle pi over 6 is 5 pi over 6. My second answer is in the tangent quadrant. We know that cosine is also negative there. To find that angle, I start at pi and I add pi over 6 to end up in the tangent quadrant. Again, making a common denominator, I find two answers. If you want to check your work, you could put this into your calculator, make sure it's on radians, take cosine of this angle and cosine of this angle, and you'll find that it's equal to negative root 3 over 2. Here's an example using a reciprocal trigonometric function, cosecant. So no different. First thing, let's isolate for cosecant of x. Doing so, I find cosecant of x equals to 2. We can't put that in our calculator because that function is not on our calculator. So we're going to have to change it back into our primary trigonometric ratio. We know that the reciprocal of cosecant is sine. So taking the reciprocal of both sides, this turns into sine of x, and this side turns into 1/2. Once again, that's a special ratio. It comes from my special triangles. Specifically this one. If you look at pi over 6, its opposite is 1 and the hypotenuse is 2. Sine of pi over 6 is 1 over 2. We've already found one of our answers. One solution to this is pi over 6. Sine of pi over 6 is 1 over 2. That's the answer in the first quadrant, or the all quadrant. Now we have to find the second answer. Because this is a positive ratio, my second answer will be in the sine quadrant. Once again, we draw our reference or related acute angle relative to the x-axis, and we have to work backwards to find this angle with related acute angle pi over 6. That's given by pi subtract pi over 6. Same answer we got there, 5 pi over 6. Finally, let's see an example where we have to use our calculators. So 5 tan of x equals 2. First off, I isolated for tan of x, 2 over 5. We know that to isolate for x here, we do the inverse operation on the other side, tan inverse. Once again, make sure your calculator is in radians. We're working in radians. When I take tan inverse, my calculator told me that the answer is 0.381. That's the answer in the first quadrant. Now, unfortunately, your calculator can only give you one answer. It's your job to find the second answer. Because this is a positive ratio, my two answers are in the all quadrant and the tangent quadrant. Once again, to get an angle in the tangent quadrant, I start at pi and I add the related acute angle. So I take pi and add the angle I found, 0.381. Final answer, 3.52. Those are my two answers to that equation. So remember, a quadratic equation is an equation with a little squared somewhere. It's got degree 2. So notice that this little sine x has a little 2 right up there, which means sine of x, the entire thing, is squared. The easiest way to solve this is to make a substitution. I can replace each of these sine x with some other variable, say w. So Everywhere I see a sign of x, I've now got w. Instead of 2 sine of x squared, 2w squared plus sine x is now w minus 1. This you should know how to solve. It's a quadratic equation, just like grade 10, 11. We find something which multiplies to -2 and adds to the center coefficient 1. Those numbers are +2, -1, and so on. Factoring, we find that this factors to this. And solving, we get w equals to -1 and w equals to 1/2. But sadly, our work is not done yet. We need to go back and replace the w with the sign of x. W does not equal to -1. We want sine x equals to -1 and sine x equals to 1/2. Now it's simplified to a linear trigonometric equation. You have to ask yourself, sine of what angle is -1? This is a special one. If you remember the sine graph, it has 5 key points at 0, pi over 2, pi, 3 pi over 2, and 2 pi. Those are the spots where sine is equal to 0, 1, 0, -1, and 0. So this is a rare example in which there's only one solution to this equation. Sine equals to -1 at only 3 pi over 2. You can see so from the graph. This is a special ratio. It comes from our special triangles. If you recall, the 30, 60, 90, or pi over 6, pi over 3, pi over 2 triangle. Sine of 30, or sine of pi over 6, equals to 1/2. That's our first answer to this equation. That's the answer in the all quadrant. But don't forget, there is a second answer in the sine quadrant. Once again, to get that, we're at pi. We have to go back pi over 6, related acute angle relative to the x-axis. And our final answer is 5 pi over 6. 3 solutions to this equation: 3 pi over 2, pi over 6, and 5 pi over 6. Our compound angle formulas are useful if we want to find the exact value of the sum of two angles. So say I know sine of some angle A, sine of some angle B, cosine of some angle A, and cosine of some angle B. I can find sine of the sum of those two angles using this formula. We've got our addition formulas as well as our subtraction formulas. These formulas, our double angle formulas, may be easily derived from the compound angle formulas if you'd like. They tell me that if I know sine of some angle and cosine of some angle, I can get the exact value of, say, sine of twice that angle, or cosine of twice that angle, or tan of twice that angle. So we'd like to determine the exact value of sine of 7 pi over 12. If you're still not really comfortable with using radians, it's 105 degrees. 105 degrees can be broken down into 2 nice angles from our special triangles, the 30, 60, 90, 45, 45, 90 triangles. 105 degrees is 60 plus 45. 60 in radians is pi over 3, and 45 is pi over 4. So I've broken down this angle into 2 nice angles, angles in my special triangles. Now, because I'm taking sine of 2 angles added together, I can use my addition formula for sine. Sine of A plus B is equal to sine of A times cos of B plus cos of A times sine of B. And that's what we've got here. Sine of the first angle times cos of the second angle plus cos of the first angle times sine of the second angle. Now each of these can be evaluated using our special triangles, which I'm sure you have memorized by now. Sine of pi over 3, or 60 degrees, is root 3 over 2. Cosine of pi over 4, or 45 degrees, is 1 over root 2. Cosine of pi over 3, or 60 degrees, is 1/2, and sine of pi over 4, or 45 degrees, is 1 over root 2. Now multiplying our fractions, we get root 3 over 2 root 2, and over here 1 over 2 root 2, and finally we've already got a common denominator. All that's left to do is add the numerators, and there's our final answer. The nice thing about this is you can always check your work. Put sine of 7 pi over 12 in your calculator. Put this giant number with all these radicals in your calculator, and just make sure that you get the exact same decimal answer. Over here I have another example using the compound angle and double angle formulas. So say I know some mystery angle x, no use in finding what that angle is. Sine of that angle is 45, and I'm told that that angle is in the first quadrant between 0 and pi over 2. And then I have some second angle y, such that sine of y is -12 over 13. Notice it's negative because it's in the fourth quadrant, the cosine quadrant. So first I'd like to find sine of the 2 angles added together. We're not going to bother finding what these angles are. They are not nice numbers. They're not nice whole numbers or our nice angles from our special triangles. We're going to use the compound angle formula. When I take sine of two angles added together, it expands to that formula, as we saw earlier. I know sine of x, it's right there. I know sine of y, it's right there. What I'm missing is cosine of y and cosine of x, so I have to do a little bit of work first. Remember that the definition of sine is opposite over hypotenuse, so what I'm missing in both of these instances is the adjacent side of the triangle. So I've sketched them right here. Here's my angle x in the first quadrant, as you were told. It has opposite 4 and hypotenuse 5, 4 over 5. By my Pythagorean theorem, 5 squared minus 4 squared, we get 3 as the missing side, the adjacent side. Because I'm in the first quadrant, cosine of that angle is positive 3 over 5. It's the all quadrant, everything's positive. I did the exact same thing over here for angle y. Remember, angle y was in the cosine quadrant, the fourth quadrant. If the opposite is 12 and the hypotenuse is 13, again, using your Pythagorean theorem, we'll find that this adjacent side is 5. Therefore, cosine of this angle y is adjacent over hypotenuse, positive 5 over 13, because we're in the cosine quadrant. Now that I have all those things, it's just a matter of slotting them in to my equation. Sine of angle x, cosine of angle y, cosine of angle x, sine of angle y. Again, multiplying our fractions and adding, we get a final answer, negative 16 over 65. Notice I never evaluated what the angles were, I just worked with the ratios. In the second example, I want to find sine of twice this angle y. So again, I'm given sine of y is negative 12 over 13. We found cos of y earlier, so using the double angle formula, which says sine of twice of an angle is equal to 2 times sine of the angle times cos of the angle, once again, just slotting in sine of y and cos of y, we get our final answer, negative 120 over 169. Identities. So first off, what's an identity? It's an equation that is true no matter what you plug in for the variable. Left side always equals right side no matter what. So trigonometric identities, we're going to prove left side equals right side with trig functions. So some tips before we get started. Unfortunately, there's no fail-proof formula that we follow. You just kind of have to try. But these tips will make things a little bit easier. First, you want to separate the left-hand side and the right-hand side. We have to keep them separate because you can't assume that the identity is true. You have to say maybe it is, maybe it isn't, separate the two sides and show that they are true. Pick the uglier side, the more complicated side, and try and make it look nicer. It's easier to make two things into one or turn fractions into smaller fractions or turn bigger things into smaller things. Don't pick the little small side because you're not really sure what you're going to do. Get rid of your reciprocal trigonometric functions. Cosecant, secant, cotangent, they're not as useful. Turn them into sine, cosine, and tangent. And lastly, if you're stuck and you're not sure what to substitute and what to try, it's probably factoring. You're probably able to factor it and cancel some stuff out and simplify that way. These identities are the ones that come up most often. You're also going to use the compound angle formulas from earlier, the double angle formulas from earlier, but these are the key ones that usually get the job done. So let's try an example. So we've got our left side, this big fraction, and this right side, a much simpler thing. So tip 1, separate left side and right side. I've rewritten left side over here, right side over there. Which one is messier and more complicated? This big fraction. I'm not really sure what I would try on that side. We could try tan of x is sine x over cos x, but then I would be stuck. Whereas on this side, I see a few things. I see cos squared and sine squared. That reminds me of my Pythagorean identity. I see that there's some stuff common to the numerator and the denominator. So this is a case where factoring will do it most quickly. There are other ways to do it. That's the other nice thing about identities. There's no right or wrong way. As long as you get left side equals right side in the end, that's all right. So I notice that this numerator is a difference of squares. Something squared minus something squared, which means it's factorable. And I also notice in the denominator, I have cosine in both of these big terms. This is factorable, both the numerator and the denominator. So here I factored the numerator into a difference of squares, cos x plus sine x times cos x minus sine x. And in the denominator, I pulled out a cosine x. You can check for yourself if you distribute, you would get that same thing back again, cos squared x plus sine x cos x. You'll notice we have a common factor, cos x plus sine x and cos x plus sine x. So in the next line, I've crossed those out, canceled them out, and I'm simply left with this big factor over that factor. We're not really getting much warmer. I still only have cosine and sine over here and a tan over there. How am I going to get there? We can't factor. It's not obvious that I can replace anything, so this is just algebra. We have to think about how we can separate this into something that looks like that. I notice there's a cosine over cosine here, which does equal to 1, and I've got a 1 there. So I've broken this fraction apart into two fractions. We're allowed to do this. This over the denominator minus this over the denominator is equivalent. If you were to bring this back together again, you'd get that with this common denominator. Now we're there. Cos x over cos x just equals to 1. And here I have my quotient identity, sine of x over cosine of x equals to tan x. And then we say, therefore, left side equals right side. It's proven. So once again, first step, separate left side and right side to two separate parts and do each one individually. So you'll notice I did a bunch of work on both sides. Unlike the last example, we only worked on one side. But here there's some work to do on both. Because I have reciprocal functions on both, just get rid of them. So over here, cosecant is the reciprocal of sine. And so I flipped it over and turned it into 1 over sine of 2 theta. Now if I come back to the left-hand side, I want to only have sine at the end of this whole process, which tells me I'm not going to replace cotangent with 1 over tan. Let me try replacing both of these with sine and with cosine. Once again, because I only have sine on that side, I want to get rid of this tan and this cotangent. Now I've got cos theta over sine theta, that's what cotangent equals, and sine theta over cos theta is tan theta. Now, I have two things on this side, two big fractions, while I only have one sort of big fraction on that side if I bring it together. So that tells me I'm going to want to bring these together. Turn two things into one. Much easier to turn 2 into 1 than break 1 into 2. In order to add these, I need a common denominator. The denominator here is sine theta and here is cos theta. So the best we're going to do is just multiply the two together. My common denominator is sine theta cos theta. So don't forget to also multiply the numerators. Because I added a cos theta here, I'm going to multiply cos theta on top. And because I multiplied by sine theta in the denominator, I multiplied by sine theta on top. Now that I have a common denominator, bring it together. This should make us happy every time we see cos squared theta plus sine squared theta or sine squared theta plus cos squared theta. Pythagorean identity just equals to 1. This side is as simple as it's going to go. I think I'm done here. I have no idea what else to do at this point. So let's see where we left off on the right-hand side. We were here, 2 times 1 over sine 2 theta. Whenever you see 2 theta, 2x, that's double angle. I replaced this with my double angle formula. Sine of 2 theta is 2 sine theta cos theta. And now notice I have a 2 up here in the numerator and a 2 in the denominator. I've canceled them. There we have it. Left side equals right side. It's proven.